So this is the second of these videos I've made, and they both go with this GitHub repository that I've got that includes a Rust library that's used to automate some electronics experiments. And in this second example, I'm going to use it to automate the comparison of two different oscillators. So up here I've got a GPS disciplined oscillator, and so what this does is it's got some kind of oscillator inside, probably quartz, and it uses the GPS signals to adjust it to keep it at exactly 10 megahertz. And so the output of this is going to channel 1 of the oscilloscope. And then down here I've got the waveform generator that can create sine waves or square waves or all kinds of waves at a lot of different frequencies. So I'm going to put this to a nominal 10 megahertz and see how it compares to what the GPS discipline oscillator produces. So I'll start by giving power to the GPS disciplined oscillator, and I'll turn this on also and put the oscilloscope on normal so it'll just continuously collect samples. So you can see already that these are both nominally 10 megahertz, and it doesn't have a lock on the GPS discipline oscillator yet, so it's not fair, I guess you could say, to evaluate it yet. But right now you can't see channel 1 because channel 2 is in the way, so I'll change the amplitude like that. So those amplitudes are the same, but the scales are different. And you can see how even though they're both nominally 10 megahertz, the frequencies are not just different, but they're varying also a little bit in time. So the sine wave coming out of the waveform generator is now a little bit closer than it was before to the sine wave produced by the GPS disciplined oscillator. And so as they heat up and settle on a steady state, that frequency will vary just a little bit. So we'll give them both some time to warm up, and also give this thing a chance to acquire some signals, and then come back in a few minutes. So now these two oscillators have pretty well reached steady state, and their frequencies relative to each other haven't changed that much in the last few minutes. So they're both still nominally 10 megahertz. And now the GPS discipline oscillator has a GPS lock, so that's what this LED in the middle indicates. And so they're still shifting in phase relative to each other, which means that they're not the exact same frequency. And how much the phase difference changes with time is what the frequency difference is. So if you look at the oscilloscope and just see how much the phase changes with time, it's somewhere in the range of maybe 1 to 5 hertz or something like that. So if we want to measure these two more precisely than that, the first way you might think about doing that is zooming way out and acquiring both of these together. So you'd want to get kind of close to the minimum Nyquist rate. So you'd get close to where you're sampling at least twice per cycle, but not many more times than twice per cycle. And so that might be the first way you'd compare the frequencies. Just sample the two, do a Fourier transform, and see where the peak is. But if you do that, it turns out that for this oscilloscope and 10 megahertz sine waves, the best you can do is using that method is to distinguish in increments of about 35 or so hertz, 35 or 40 hertz, which isn't good enough because, as you can see when we zoom in close, the difference is probably less than 5 hertz between the two. So we're going to have to come up with some kind of other way to do it, and I'll explain in a minute how we do that. But before we do that, it's worth making the point that we're not actually proving that one's right or one's wrong here. We're just showing that they're different. So right now we've got the channel 1 sine wave is what we're triggering off of. So that one stays fixed on the screen, and then the other one's moving. But we could have also triggered off channel 2. So we're not showing that one's right and one's wrong. We're just showing that they're different. And so if you want to think about how you could evaluate one of these GPS discipline oscillators to see whether or not they're they're keeping the same time. What you could try to do is just use two of them and compare the two, just like we compared the GPS discipline oscillator with the waveform generator. And then if they're both referencing the same GPS system, they should settle on the same frequency. So that's what we'll try next. We'll set that up and be right back. So now we've got a similar setup, except instead of having a GPS oscillator and the waveform generator hooked up to the oscilloscope, we've got two of the same model of GPS oscillators hooked up. And they both got a lock now. That's what that middle light indicates. But you can see the frequencies still vary just a little bit. You can see the phase drift really slowly relative to each other. So right now they're about 45 degrees out of phase, and they're coming close to 90 degrees out of phase. So yeah, there it goes. So now they're about 180 degrees out of phase. So right now the frequencies are very, very close, but they're not quite exactly the same. So let's check back in a little while and see how they look later. So these two oscillators have had about 2 hours now to kind of settle, and it looks like they're extremely close to the same frequency now. Like, it's almost impossible to tell just with the naked eye the difference. There's still a little bit of residual phase drift, and they're so close now that phase drift is a more appropriate term, I think, than frequency difference. But if I use the cursor to mark the point where they cross zero, so it crosses zero, the channel 2 crosses zero back here, channel 1 crosses zero here, and so that's about 32 nanoseconds now. And you can see just very, very slowly it drifts a little bit. So over here where we marked it crossing zero, it's drifted maybe a fraction of a nanosecond so far. So there's still a little bit of residual drift even when these are super close to each other. So if you wanted, depending on what you're using it for, maybe that little bit of residual drift that's still there after 2 hours matters to you. So if you're using it for something where that does matter, then you might want to ask questions like how close does it eventually get to zero? How long does it take to get there? How consistently does it get there in this amount of time? And stuff like that. And those are things that would be really tedious to measure by hand. You're probably going to want to also measure it more than once. So this is a really good use case for this code that automates these kind of measurements. So we want to be able to measure really small frequency differences and these really small phase drifts over time. And so to do that, we're going to have to make some hardware that makes that a little bit easier. And so here in a minute I'll show you what we're going to use to do that. So this is what we're going to use to measure these really small frequencies differences. So this is basically just a bunch of 12-bit binary counters organized into two chains, one for each of the oscillators that we want to compare. So we've got a color coding system here to where blue is the clocks, the two clocks for the two chains. Brown wires here represent ground. The white wires you see represent the plus power voltage, so that's going to be plus 3.3 volts in this case. And then these each have a reset pin also, so these orange pins represent, these orange wires represent reset. So the reset on the left chain and the right chain are connected together, and so the entire reset bus all connects to all the pins on all the counters, and they meet here where there's a 50 ohm resistor that connects the reset to ground. So this is reset by a high voltage on the reset lines. So what we do is when we want to reset it, we just apply a high voltage to anywhere where one of these orange wires connects, and then that'll pull the voltage high and it'll reset the entire thing. And then when we take out that high voltage, this 50 ohm resistor will pull that line down to ground, so that voltage will never be floating. It gets by default, when there's no high voltage connected anywhere to any reset pins, this 50 ohm resistor pulls it down to ground, so that way you know, like I say, it's never floating. So the way this basically works is that the clock pin for each of these counters is the second from the bottom on the bottom right. So you see clock 2, which will be the second oscillator that we're comparing. It connects to the first counter's clock terminal, and then there's a bunch of bits that represent the current count on the chip, and then the most significant bit is this one in the upper left, and then this one connects down here to the clock pin of the next chip, and then there's a bunch of pins that we're not interested in that just count all the different bits, but the one we need for our purposes is the most significant bit again, which is again the one in the upper left, and then this one connects down here to the clock pin of the next one. And then we're not actually going to use all the pins on this last one. We're going to stop with this one, and then by the time we get here, what ends up happening is that we originally have a 10 megahertz clock input here, and then by the time we get here, we get a square wave that goes through a full cycle once every 13.4 seconds. And so what we can do is we can reset this entire thing all at once and then let it go, and then we can trigger the oscilloscope based on one of these two channels, and then once it triggers we can just see what the difference in time is between these two lines, and then that'll tell us what the phase difference is over that 13.4 second interval like this. So we're not even limited to integer multiples of a clock cycle. If we're just limited to the sampling interval of the oscilloscope, so we can measure some really small frequency differences this way, and that's basically how it works. If we wanted, so the only real limitation, or one of the main limitations, I guess, of this is that we're limited to, we can measure some really small frequency differences, but we're limited to averaging over a 13.4 second interval. So for this case, that's going to work fine, because from the initial tests we did just looking at the oscilloscope, the frequencies don't change much over that time interval in the case we're interested in. But that's basically how it works. So these green wires are what are going to come out and actually connect to the oscilloscope to do that comparison. So every 13.4 seconds we'll get a rising signal on both of these chains, and it'll be offset by some pretty small length of time, and then that length of time and then how it changes from one cycle to the next will tell us how the phase is varying between the two chains. So now everything's powered up, and I'm going to show you how it works with just one of these two chains. And the way it's going to work is that one channel of the oscilloscope is going to be connected to the original clock, the actual GPS oscillator, and the second one will be connected to the second one I'm going to move around to show you how different pins work. So right now they're connected to the same, I've got channel 2 connected to the input of the first counter, so it's reading the exact same thing. So I'm just going to make the clock a little bit smaller like that, so that we can see channel 2 a little bit better as we move it around. So if we move this up to the next significant bit, right above the clock on the first one, we can see that we've cut the frequency in half. So it used to, so if we look at one rising cycle to the next, and we're triggering off channel 2 now, so it's a little bit easier to see these kinds of things. But when channel 2 goes through one full cycle, channel 1, which is the clock, goes through 2 whole cycles, so it's cut the frequency in half. And then we can just keep working our way up. So I think this is so you see, I think this is 4 complete cycles per one cycle of the bit we're looking at on channel 2. So this goes through one full cycle, and in that same time we go through 1, 2, 3, 4 cycles on the clock. So we could just keep working our way up like that, and we just keep dividing the frequency in half. I'm not going to look at all of them, but see here we get a square wave. This is pretty close to the end of the first counter, and then this is in between the first and second counter. So by the time we get here, going through one complete cycle of this square wave takes 410 microseconds. So we can just kind of work our way up on that second counter, and the frequency keeps getting smaller and smaller, and the pulses keep getting longer and longer. And this is what it looks like in between the second and third counter. So you see now it takes much longer to go through one complete cycle. So when I put it in that roll mode, it's scrolling across in real time, so you can see how slow those pulses are now. So right now, one complete cycle of this square wave is 1.69 seconds. And so the one we're actually going to read when we're comparing the frequencies of the two oscillators is this one. So now it's still scrolling across in real time, so you can see it's much slower. So that's high for 6.76 seconds, I think, something like that. And the complete high to low cycle is going to be about 13.4 seconds. So if I measure the high and the low portion of one cycle, yeah, that's 13. So now I've got the two channels of the oscilloscope hooked up to the outputs of the two chains, and the inputs of the chains are hooked up, one of them to one of the GPS oscillators, and the other to the waveform generator, generating a 10 megahertz sine wave. And I hooked it up that way because the frequency difference is going to be a lot more obvious between those two than between the two GPS oscillators, so it'll be a little bit better for demonstration. So I'm going to start by resetting the whole thing. So I'm going to connect the reset wire to the high voltage and then just release it, and that 50 ohm resistor will pull it back down to ground, and that'll start the counters counting. So I'm going to use the first time it triggers, I'll use the right cursor to mark where channel 1 was. And then the second time, I'll use the left cursor to mark where channel 1 was. And channel 2 is in the same place every time because we're triggering off channel 2. So the difference in time between these two is 4.16 microseconds. So we can do the math on what frequency difference that ends up being. So this will be how we figure out the frequency difference over that interval. So we start with the change in time between the two captures. So that was 4.16 microseconds. And I'm going to put the units off to the side so we can check it as we go. So we want to know how many cycles off we were, so we can multiply that time by the rate of the clock, the nominal rate of the clock. And this is seconds times cycles per second, which is cycles. So 41.6 cycles, and they were 41.6 cycles off after 13.4 seconds. So this is cycles divided by seconds equals hertz. So this should be the frequency difference over that time interval between the two oscillators, and it comes out to about 3.1 hertz, which is about right. That's kind of what it looked like when we looked at them on the oscilloscope earlier. So this makes sense. So this is the complete setup that's actually running right now, and the way it works that's different from the last setup we looked at is that the two GPS disciplined oscillators are connected to the DC power supply, and that's at channel 2. And the good thing about that is that we can apply power to both of them at the same time, and it also makes it easier to make sure that they have a common ground with the rest of the system. The ends of the two chains are still connected to the two channels. The end of the two chains are still connected to the two channels of the oscilloscope like we saw before. And then one of the differences now is that the whole thing is controlled by the Raspberry Pi. And one of the cool things this illustrates is that Rust works really well for these embedded resource-constrained environments like this. Some other languages with heavy runtimes like Python will work if you insist, but Rust is really still in its element in these kind of resource-constrained environments because it's got almost as little runtime as you can realistically expect, and it's just as light and fast as C in these cases. So it's kind of nice if you are running some kind of experiment where you want to set it up and leave it and run it on low power for a long time. You can just dedicate a small little controller like this to it. But it's not. We're not using it just to illustrate that. We're also using it because the code needs to be able to reset the counters periodically, and so it does that using one of the GPIO pins on the Raspberry Pi. So you can see that connected with the orange wire going across. And then next we'll take a look at the code that's actually running. So this is the output of the whole thing. It's the plot of a couple different runs, and we're plotting the frequency difference between the two oscillators as a function of time since turning on the power. So we can see that they start when you first power it on being off by about 6 hertz or so. And if we zoom in on this early region here where they're converging pretty quickly, we can see that it gets down to within 1 hertz or so of each other by about 2 minutes, or for sure by 3 minutes. And then if we zoom in a little bit more on this kind of longer term region, we can see that for one thing there's some little spikes here and there, but then also we can see that the worst those get is about 0.1 hertz. And then if we zoom in on this stuff here, we can see that it, for the most part, gets about as good as it's going to get around 40 minutes or so, and that's about 0.02 hertz. And then maybe it gets a little bit better after that, but it's pretty close. So depending on what you're using it for, you could use this data to evaluate whether or not it'll work for you. But what you actually use the data for is a little bit beside the point for this. The point for what I'm trying to show here is that each of these dots is one iteration of that whole process where we manually measured the difference in the two rise times and then figured out what the frequency difference was based on that, comparing it between two triggers. So you can imagine that getting all this data manually by hand would be pretty impractical. So the only way to get something similar to this is to automate it. And so next we'll look at the code that actually did it and see how it works. So this is the code that actually runs the experiment, and I think it might be a little bit longer than the previous example, but it's still pretty short. It's only 130 lines or so. So up here at the top we've got all the imports and everything, and then below that we define a struct that we use to store the trigger result. So every time the oscilloscope triggers, we produce one of these. And then below that we've got a function that resets the counters. And it does this, like I was saying when I was showing the setup, it does it by pulling one of the GPIO pins high. So it pulls it high and holds it for 1 second, so plenty long enough and then brings it back low, and that's what resets the entire set of counters. This is the actual main function here. So we start off by checking to make sure we're on a Raspberry Pi, that we can interface with the system on the chip and the GPIO pins. And then below that we get an actual interface to the GPIO pins, and we're interacting with a pin that we defined using this constant up here. So like I was saying, one of the cool things about Rust is how well it works on embedded resource-constrained environments like this. And it does that mostly because in higher-level languages that have a heavy runtime, a lot of that heavy runtime is memory management, and most of that is a garbage collector. And before Rust, garbage collection was one of the few ways to achieve kind of consistent memory safety, but Rust is kind of cool because it achieves memory safety without a garbage collector. So it's memory safety with a really light runtime. So it's kind of the best of both worlds, kind of the best of lower level languages like C, and higher level languages like Go or Python. And there's a cost to that. The cost is that there's a really challenging type system that you have to learn, but if you put the time into learning it, it really pays you back for it. But anyway, that's where we get the interface to the GPIO pin that we use to reset the whole thing. We've got the IP addresses for the two hosts. So this is the DC power supply and the oscilloscope. Then we create the two structs that we actually use to interface with them. And we'll start by getting the full state of the DC power supply, and then we output it to the screen. There's no functional... that doesn't affect the... It's got nothing to do with the final output. That's just for awareness. It posts debug information like that. It sets the voltage for the two channels, even though it's already set the way I ran it. And then it sets the current limits. You could set it up to where the program controlled the outputs, so it could turn the oscillators on and turn them off. So if you wanted to run a lot of experiments over a long time, you could kind of automate it that way. For the actual unit I was having a little bit of trouble getting it to work consistently. So since I only needed about 10 or 12 runs, I just did it manually. So here we record the start time for the whole experiment. We set up some of the parameters for the oscilloscope. This function just tells us that it tells the oscilloscope that when we ask for the waveform, we want the whole thing, is basically what that does. And then we start the experiment by resetting the counters right here. And then we're going to continually keep track of the most recent reset time, and we're going to use this vector to accumulate all the results of all the triggers. And so the length of the experiment is defined by this max records constant that I created up here. And so I set it to 600, which at the rate it triggers ends up being about 2 hours worth of data. And then then for each of these records, we just set the trigger mode to single, so that'll capture a waveform on the two channels. We wait for it to finish. We record the time since the last reset and the time since the start. And then we also next we actually transfer the two waveforms that we just captured. Record the actual sample rate. This shouldn't change from one iteration to the next, but it's so quick and easy, just to be sure, might as well capture it every time. And then we find the midpoint, the vertical midpoint, and so that allows us to identify where the two channels cross the midpoint. And then there will always be a transition for channel 2, because channel 2 is the channel we use to trigger, but there might not always be one for channel 1 if it goes out of view, out of scope, either left or right. So if that happens, then we just reset the counters, reset the variable that keeps track of the last reset time, and then we don't record this sample. But if that's not the case, which is most of the time, and both transitions are in view, then we just capture the sample number where channel 1 crossed, capture the sample number where channel 2 crossed, and then the time difference between the two is just the number of samples divided by the sample rate. And then all this stuff in here doesn't affect the output, it's just debugging information that it prints to the screen so you can see it scroll while it's running if you want. And then we just store all these results in this vector that's accumulating them all. And then once we've got the number of records we want, then we just come out here and print the results to standard out, and then turn off the power to the oscillators, and then we're done. So this is the only place where it actually outputs it to the standard output pipe. Everywhere else, we're using this ePrint line, which outputs to standard error instead of standard out. So that allows you to, if you're using Linux or a Unix-based system, you can pipe it to a file without getting all this other stuff in there too. So you just end up with a JSON file if you do it that way. But that's it. It's a pretty cool example of how you can automate something that would otherwise be pretty tedious, and it's all memory safe and lightweight, and it's pretty cool. Thanks for watching, and watch for more of these. Thanks.